We are Team 16 sharing our final project for the analysis and redesign of an automatic pet feeder. Team 16 is made up of Miles, Chris, Stephanie, Teresa, Brittany, and Andrew. This product is an automatic pet feeder that dispenses a set quantity of food at pre-programmed times. The user pre-fills the container with a preferred dried pet food and the feeder does the rest. The primary customers are cat owners, while the secondary users are dog owners, kennels, and pet hospitals. The annual demand is estimated at 500,000 per year, and the estimated production volume is 100,000 per year.
The core function of the pet feeder is to nourish the pet, whereas sub-functions include containing the food, delivering the food to the bowl, and ensuring the product is convenient and dependable.
As shown in the function component mapping matrix, more components support the primary function of dispensing food than any other function, revealing opportunities for part consolidation. The redesign focused on the feeder housing, feeder chute, and supply flange, as they also share the function of position food. Furthermore, the motor attachment was investigated to see if the housing could be designed to incorporate the mounting of the motor. After comparing the functions on the FAST diagram with our primary and secondary customer groups, only the adjust portion function is different. The unique components that relate to this function are the storage container and food bowl. The common interface for the storage container is the supply flange, and for the bowl is features on the faceplate. These interfaces were also optimized to support the redesign of the plastic feeder assembly and metal food bowl.
The design for manual assembly analysis was completed by selecting the feeder housing and feeder chute as platform parts, and the storage container as the module part. From the quad chart, the parts in the high functional importance and high manufacturing cost bucket are all purchased electronics, so our focus is on optimizing parts with high functional importance and high assembly time that will be shown on the next slide. On the left side of the slide, the feeder housing and feeder chute were combined, which resulted in reduced part count, reduced fasteners at their interface, and reduced part variety by reducing fastener proliferation. On the right side of the slide, the supply flange was combined with the storage container, which resulted in reduced part count, reduced fasteners at their interface, implementation of snap fits, and reduction of fastener proliferation. In addition to combining the feeder housing with the feeder chute and combining the supply flange with the storage container, the motor mount was also removed, as well as 10 screws were eliminated through part combination and implementation of snap fit interfaces. These modifications resulted in improvement of assembly time from 276 seconds to 164 seconds, and assembly efficiency from 14% to 18%. After these changes are implemented, product functionality will remain unchanged, and manufacturing costs will be reduced as a result of fewer total parts, decreased assembly time, and increased efficiency.
A design for automated assembly analysis is completed based on the platform subassembly that is made up of the feeder housing, flywheel, and feeder chute. They are justified as they have a high importance in the quad chart. A high functional importance with high manufacturing cost part was not selected as those parts are considered electrical components. The pre-automated assembly analysis has a total handling and insertion cost of $106.56. After redesigning the parts, the handling and insertion cost reduced to $71.64 per part. This slide shows the before and after of the automated assembly analysis. You can see how the part count was reduced by combining the flywheel housing and feeder chute. This combination also reduced the number of fasteners by removing the need for unique fasteners in this subassembly. Additionally, with the reduction of total amount of screws, DFA 12 is addressed by reducing the need to reorient the part during assembly. These changes did not impact the product function but improved the manufacturing process.
The plastic part redesigned was the combined feeder housing and feeder chute, since they shared the same key functions from the component mapping matrix. The key dimensions are the locations for the motor mount screw holes. While a general tolerance of plus or minus 0.5 millimeters is standard for plastic parts, the screws have to align through 3 surfaces, so we selected the next tighter tolerance of plus or minus 0.35 millimeters. Both parts are to be made from polypropylene. Based on shape, tolerance, and other attributes, the possible manufacturing processes compatible with polypropylene were narrowed down to machining, injection molding, and blow molding, out of which injection molding was selected.
Analyzing the feeder chute and housing assembly using the parting line shown in the top right, we estimated the piece price to be right around 39 cents. The part had a volume of just over 37 cubic centimeters and a max wall thickness of 4.6 millimeters. The team also anticipated the critical dimensions of the motor mount holes, needed a tighter tolerance of plus or minus 0.35 millimeters. The max wall thickness, however, creates quite a long cooling cycle, so the team then ran it through DfM Pro, where there are multiple recommendations shown on the left-hand side for sharp angles, adding more draft angles, and ensuring the walls were uniform thickness. After taking into account the DfM Pro recommendations, the team redesigned the whole piece to have a thinner, uniform wall. The biggest changes for the wall uniformity came around the motor mount holes. The team also revised around the flywheel opening and chute to increase the radii to assist with the draft angles, as well as avoiding sharp corners. The largest change, however, for the part was definitely revolving around the max wall thickness. After finding and reducing the areas causing the non-uniform wall thickness, our new max thickness was only 2.54 millimeters. This reduced our cooling time significantly, leading to a much cheaper operating cost and resulting in a cost of only about 22 cents per piece. This is a 17-cent reduction in cost by following DFIM 1, 2, 3, and 4.
The feeder bowl is a stainless steel component that can be made using either a sheet metal working or machining process. The shape and specifications of this specific component align better for the sheet forming process. The preliminary bowl design was analyzed using the DfM Pro software, which highlighted some tight bend radii on various features in the bowl relative to the material thickness. These features were not meeting best practices of avoiding sharp corners and sharp bends for the sheet metal worked parts. This component requires blanking, bending, and forming dies to make and has an estimated cost per part of $2.98 with an assumed volume of 100,000. The finalized bowl design incorporated a minor overall size reduction and thickness reduction and implemented some more forgiving radii on the corners per DfM Pro recommendations. The key dimensions in the bowl design are the size and location of the tabs that attach the bowl to the feeder housing, which enables the bowl to be removed, cleaned, and replaced easily by the owner. The updated part design requires the same dies, but the reduction in material cost drove a total cost reduction of 81 cents per part. The pre and post DfM designs were quoted online to compare with the analytical calculations. The key takeaway to note is the reduction in cost between the pre-DfM design and the post-DfM design aligns with the hand calculations. A few caveats to note are that the Hub's online quote was using machining as the process instead of sheet metal working, and the max quantity of parts that could be quoted was 150, which is few orders of magnitude less than our projected volume of 100,000, which adds a lot of error in the extrapolation.
As an enhancement to our device, we would include an app for pet owners to help guide them. In the instructions, after purchasing the pet feeder, the user is guided to download the free My Pet app from the Apple or Google stores for the user's phone. The pet feeder can be programmed from the screen or from the app on the phone and allows users to modify the operation of the device from the phone instead of having to be at the device to modify its operating parameters. The pet system would benefit the consumer financially by not requiring paying a dog sitter or someone to come over to the house to feed the pet. We could also solicit companies' interest in getting their name out to pet owners to pay for some sort of commercial space on our app. Environmentally, we help by regulating the quantity of food distributed. We are preventing overportioning and potential waste of food. In conclusion, we were able to achieve our primary goal of reducing parts to help reduce cost, our secondary goal of making it easier to assemble, our tertiary goal of manufacturing the parts at a lower cost. We improved design for assembly and reduced manual assembly by 112 seconds and lowered our automated assembly cost by almost $35. Our design for manufacturing significantly reduced piece price by utilizing material and eliminating tooling. Additionally, we would have liked to have improved access to loading food and have analyzed some of the other cost measures in the design. We also noticed the size of the pet feeder was relatively small for real-world applications. Another approach we would have taken would be to look more into less expensive electrical components and see if we could reduce and combine them in the future. Thank you for taking the time to review our presentation. We hope it was informative.